So, if your outer shells, right, are not full, right, so if you have one shell, the fullness is 2 electrons. If you have more than one shell, it's 8. So, there won't be but a few of the elements that actually have full outer shells. So most of those elements are going to want to interact in some way or another, and that interaction we call chemical bonds. So it can be a weak connection or strong electrical attraction. It really depends on what has happened, and there aren't many options for how these bonds can occur. So just try to get your mind around this. It's pretty straightforward, and again, there's not very many options. And the thing is if we want to make a complex life form like yourselves, we have to form a lot of different molecules and compounds, and they have to differ so they can take on different functions. So I say here again, molecules and compounds. I'm not going to ask you how these differ, but if it's a compound, it has to have 2 different elements. So while all molecules are going to be compounds, not all compounds will be molecules. It's not really here or there, honestly, for our understanding. So there is like molecular oxygen, O2, or hydrogen or nitrogen, H2, N2, would not be a compound, right? So, but we just really gravitate towards the term molecules to describe these when 2 or more elements are together. And I said here, there are not many choices, I've already mentioned, right? They occur when the electrons in the outer shell are either 2 choices, right? I said not many, transferred from one element to another, or shared. So we're going to talk here about then ionic bonding, when the electrons are transferred, and when they're shared, we'll talk about this as covalent bonding, right? So here's a classic example of a transfer between this metal sodium and nonmetal chloride, and each of these actually has 3 shells. They're both in the same row together. It turns out that sodium's in the first group and chloride's in the 7th group, and so what that grouping, we said, acknowledges the number of electrons in the outer shell, and here you see it. Sodium with its 11 electrons, so its atomic number is 11. Its atomic mass or mass number is 23, and which is not here or there. We're really focusing on the electrons now. But so with 11, we put 2 in the first, and that leaves 9. So 8 can go in the second shell, and that's just 1 in the outer shell, just 1. And then chloride, right, with its atomic number of 17. And its mass somewhere around 35, it's got an issue, the opposite really, right? It's with its 17 electrons, it puts 2 in there, right? So it's got 15 left over. It goes 8 in the second, and then 7, only 7 in that outer shell. Only 7, just short 1, right, in the outer shell. So it really is logical that sodium would transfer its electron to chloride, and therefore, it would then have a stable outer shell and outer electrons, because that's what electrons are right here, right? And so would chloride. So they both are balanced now. But they have an uneven number of, right, protons and electrons. Sodium is sodium, so it's still atomic number 11, but now it only has 10 electrons, so we refer to it as A plus and A plus. Chloride, its atomic number is still 17, but has 18 electrons, so it's Cl minus. All right, and these are both then considered ions. And this positive charge here and negative charge here actually attract each other, and this holds sodium together, and the sodium and chloride atoms then really align into what we refer to as a crystal because of this. And they're held together, but it's kind of a weak situation. So again, if you lose an electron, like sodium here, you become positive or a cation. If you gain an electron, you're negative or an anion. And the end result is that this positive and negative charge on these ions attracts them to each other. So both are stabilized, and they've completed the number in the electron shells. All right? So the other choice you have is sharing your electrons. So you're not giving them up, and you're not taking, and you're not giving. You both get to keep your electrons, and you allow each other to use the other's electrons. So covalence means, again, sharing, but there are two kinds of sharing here, right? So there's a sharing where the two electrons, so here we have classic, this is molecular hydrogen, H2, and each one has one electron, so when they share them, they both get two, right, in their outer shell. So they're both happy, and that's very stable, right? And they equally share. They have an equal attraction because they're both have just one positive charge for those negative charges, right? Here's molecular oxygen, and it's also very equally shared electrons. Again, oxygen here is an atomic mass, or excuse me, atomic number of 8, so you get 2 in the inner right orbital and 6 in the outer, and all it needs is 2 more. So that's indeed what it does. It shares 2 pairs of electrons. This is actually considered a double. All right, as you see here, a double bond. It's a single bond here. All right, and then there's carbon dioxide, which is also basically equal sharing. All right, and again, in each scenario, all the atoms are satisfying their outer orbitals' maximum capacity. All right. Now over here, there's sharing of electrons between an oxygen and 2 hydrogens. All right. And again, remember, oxygen we said was 8 protons, so atomic number 8. And so 2 and then 6, it just needs 2 more. Well, it can take one. It can share one with one hydrogen and one with another hydrogen, and it does. And of course, each hydrogen needs only one more, so they can share with the share with the oxygen. But it turns out that these hydrogen atoms have such a small nucleus. They only have 1 proton. They don't even have a neutron. And this oxygen has a pretty big nucleus and has a lot of positive charge. So the oxygen atom, while they are sharing their electrons, the electrons are moving around all the nuclei, they spend more time situated near the nucleus of the oxygen. So the molecule results in some polarity. Right? There's poles or dipole. There's this situation where oxygen is kind of hogging, right, the electrons for all the electrons, and becomes a little more negative. Since hydrogen can't compete as well with the oxygen, it tends to be positive because its electrons are being pulled over here. So we refer to water molecules as polar covalent bonding, holds them all together. And again, and this is really important. And really, so nonpolar, equal attraction of electrons by both nuclei, no net charge. Polar, unequal sharing, small electrical charge. All right, but in both scenarios, you have completed your outer shell just like you did when you did ionic bonding. I say here that, so that's it for the bonds that can form really between the atoms, but then there's bonds to consider between the molecules, right? And one example of that are hydrogen bonds, right? Hydrogen bonds form, right? And I said, remember from the ionic bonds that opposites attract. These hydrogen bonds form between hydrogen in one molecule and another atom in a different molecule. So you'll see here these hydrogens are attracted to this oxygen here in both cases. Why is that? Well, remember the hydrogens have positive charges associated with them, and the oxygen has a negative. So the positive charge of this hydrogen is right attracting it to the negative charge here, and the same here. So opposites are attracting. So while these bonds are not very strong, I mean, because they're not among, electrons are not being shared, electrons are not being transferred, there's simply a charge associated with this molecule and a charge associated with this molecule that attracts the two things together. So they're very weak, but it turns out there's a lot of them. There's an awful lot of hydrogen bonding in life science and in the world in general, because there's an awful lot of water, right? And so it ends up really holding and even allowing for some structural integrity large molecules. Right? Again, hydrogen is the most common element in the body and in the universe. I know it said oxygen, but really there is a lot of hydrogen, and that is that it's bound up in things, right? So the former one was talking about, this difference in amounts and masses and sizes. So the one that said oxygen. These bonds are important to the chemistry of your body. They hold all that DNA together as well, that we'll see when we look at nucleic acids. All right? We can arrange matter and energy to suit our needs, right? So, and this we do by chemical reactions. So we have atoms that are units of matter and building blocks, and they bond together in very specific ways, and then they can rearrange those bonds and rearrange the atoms to suit the needs of the body. And so the chemical reactions that govern this rearrangement just really fall into about three categories. And the two of them we really talk about more than anything. You can either start building more with these molecules and rearranging some of these molecules, or you can take them apart. So we refer to the building synthesis, right, as anabolic, and the destruction as catabolic, right? So in a chemical reaction, and here's just a real classic one, we were looking at this already with sodium and chloride bound together into an ionic bond into a new molecule and also compound, right? Because of that, here we have this rearrangement of methane and oxygen to get carbon dioxide and water, right? So when we talk about chemical reactions, the arrow points to the product, right? The atoms or molecules on the other side of the arrow, not on the other side of the arrow, on the other side of the arrow, basically, they are the reactants, right? So they're going to get together and they're going to form the product. So again, the rule is the arrow is pointing to the product, right? And then catalysts are going to be other chemicals, molecules, that would help speed up this rearrangement that either results in anabolic, building something, synthesis, or taking something apart, okay? So catalysts are not changed by the reaction, but they help the reaction. Generally, the catalysts we talk about in life sciences are enzymes. So I say here, so what has changed in the reaction? Well, the reactants have gone away. There is no more methane once we do this, right? And the oxygen is gone too. So the reactants are converted to products. But, right, what has not changed? Well, you had one carbon here. You still have one here, right? You cannot create or destroy matter. 4 hydrogens here, better have 4 here, right? 4 oxygens here, better have 4 here. So you balance these equations, and that's what a lot of chemistry uses, basically just trying to figure out how molecules and atoms get together predictably, and then making sure that you've accounted for all the matter. So, all right, what's the role of energy in this? That's a great question, because I said a lot of what we talk about centers around energy and transfers of energy. So it turns out if you want to get matter together, right, these atoms and molecules together, so that you can break and form the bonds, you need energy. All right, so it just takes a little bit of a push, in other words. And this means, right, requirement for life, which we really already addressed in chapter 1. So I just say a little bit of a review about physical science. Do you recall the difference in kinetic and potential energy? Well, if you don't, kinetic is an energy of movement. It's doing something, getting something done, because energy is the capacity to do work or bring about change. And potential energy is stored. It's not doing, but it can do. All right? Where do we find potential energy? Well, that's what a calorie is. Calories that are measured in your food are really giving you an indication of how much possible energy could be released when the bonds of the food substances you eat, like the chemistry, your food's chemicals, when the bonds are broken and rearranged. What do we call a reaction that releases energy? Okay. Well, if it's releasing energy, we actually call it exergonic. If it's absorbing energy, it's endergonic. So there's some very specific terms to describe what's happening. And ultimately, I say here, we need to figure out how to build things and transfer energy between molecules in order to stay alive.